All right, so this is the last video for the unit. This video, we're just going to be looking at some conceptual things, including the types of catalyst and also the Arrhenius equation. Now, with the Arrhenius equation, that was taken out of the curriculum, but they really just want you to understand the concepts behind it, not have to do any math with it. So this equation, the Arrhenius equation, relates the rate of a reaction to the activation energy, the temperature, the orientation factor, and the collision frequency. So the collision frequency is how often molecules will collide with each other. So for higher molecularity reactions, so basically the higher the order, the higher the molecularity. If you have a higher molecularity, you're going to have a smaller collision frequency factor. So basically, if you have like a third order reaction, you need 3 molecules to collide. You have to have 3 molecules collide. They have to be in the correct orientation, and they have to have the minimum amount of energy to get a successful collision. So with a third order reaction, it's going to have collisions that are less effective because you have to have all the molecules come together, you have to have enough energy, and you have to have the correct orientation. And so the more molecules involved in the reaction, the longer the reaction will take you. So if I have a first order reaction where it's only dependent on 1 molecule, or even a second order reaction where we have less molecules involved, those reactions will be quicker because the collisions will be more effective. Now, orientation factor is also important. The orientation factor is going to be smaller for simpler molecules. So if we're going to compare 2 reactions, let's say H plus Cl produces HCl. Well, we just have 2 atoms here. So for them to collide with each other, there aren't really many ways they can orient themselves. But if I have a molecule like NO2, like this, well, it has to be oriented in a certain way. So maybe it has to be oriented like this when it collides with the CO molecule. So maybe it has to be like this. So if it collides with the CO molecule and it's oriented like this, it won't happen. So the simpler the molecule, the faster the reaction. All right, so catalysts. Catalysts are very important because they're going to increase the rate of reaction. We would not exist without catalyst. So a catalyst is something that you can add to a reaction. It's going to stay exactly the same. So if I add I- to a reaction to increase the rate, I should have an I- at the end. It should be unchanged. Now the way a catalyst works is that it will lower the activation energy. So if this is how much energy you need to make the reaction happen, the catalyst will lower it. It'll lower the hump. And it does that because it provides a different pathway for the reaction to happen. So the mechanism will be different. So maybe it'll have less steps, or the steps are just quicker. So it lowers that minimum amount of energy necessary for the reaction to happen by providing a different pathway. So it increases the chance that the particles will have the minimum amount of energy for the reaction to happen. Now, make a note of this, delta H will be unchanged. So the amount of energy that you put into the reaction or release from the reaction will not change. Only the activation energy, the minimum amount of energy to start the reaction, changes. All right, so basically, if you add a catalyst, this is what happens. So without the catalyst, maybe you have this many molecules right here that have the minimum amount of energy. But with a catalyst, you lower the amount of energy necessary, so you increase the amount of molecules that have that energy, and the reaction happens quicker. All right, so you have a couple different types of catalyst. One is an acid-base catalyst. So basically it's like adding an acid or a base to a reaction. So the reactant's either going to gain or lose an H+, which forms a new intermediate, and that changes the reaction rate. So this is a reaction that happens normally when you have a ketone, which has this C-O-O bond right here. A ketone transforms into an enol, so it's this group right here. A carbon bonded to a double bonded to another carbon bonded to an alcohol group right here. This reaction just naturally happens. The atoms are kind of moved around in the reaction. So this will happen faster if you add an acid or a base. So at the end, you're still going to have the acid or the base. So if you add like hydronium to that reaction, you should still have hydronium at the end. It just makes the reaction happen quicker, provides a different pathway. Now, a surface catalyst is usually a transition metal, and basically you will take a gaseous reactant, so it has to be in a gas state, and the gas molecule is absorbed or adheres to that surface of the metal. Now, this works in a couple different ways. It depends on what the reaction is. If the gas molecule is absorbed, maybe it weakens the bonds in the molecules. So if you have like an H2 molecule and it adheres to the surface, it actually starts to weaken those bonds between the H atoms here. It could also work by concentrating the gas more. So if you have a gas in a container, molecules are everywhere. They're moving around. It's simply by chance that they collide and hit each other. But if you adhere it to a surface, a small surface, then they're more concentrated in one area instead of being everywhere in the container. All right, so the Harber process is a pretty important reaction. It's H2 plus N2 produces ammonia. So what happens is that these H2 and N2 molecules are adhered to the surface, and the bonds between the atoms start to weaken. So then what you have are these super reactive atoms that are atoms or maybe smaller molecules that are bonded to this metal surface, and then since they're super reactive, they start to react with each other and then make ammonia. All right, the last type of catalyst that you need to know about is an enzyme. These are protein molecules. They act as biological catalysts. So inside of your body you have millions of enzymes which allow you to function normally. So enzymes are used in DNA replication, to fix your DNA if something happens to it. They're used in almost every single biological process that we have. So the enzyme, which is just a catalyst, has something called an active site. And that's where a substrate, which is just a reactant, binds to it. And what it does is it makes a new intermediate, so it provides a new pathway to lower the activation energy. And a lot of times biology classes will tell you it's a lock and key model. So only one substrate can fit into the enzyme. That's not always true. Okay? You can have an induced fit, you can have other things happen. You can actually fit other substrates in a lot of enzymes. Most of the time it is a lock and key, but not always. So what you see with an enzyme is that you have an enzyme will bond with a substrate or multiple substrates, and sometimes it will weaken the bonds in between the molecules. It'll split them up, or you could put multiple things and put them together. So yeah, usually it's a lock and key where it just kind of fits into place, but it's not always like that. And this is what it would actually look like if you were looking at the molecular level. All right, and I'll see you guys in class.